In today's video, we will see a revolutionary approach to use a large language model to operate on a visual environment. The training method has powerful applications to complex domains that can benefit from imitation and transfer learning. Join me. My name is Santiago, and I explore big ideas in AI. This is our fourth and final video in our planning series. Today, we'll be exploring the topic of multimodal planning with large language models. It is based on the paper Embodied Multi-Modal Agent trained by an LLM, or EMA in short. By now, you may be familiar with visual ALF. Well, actually, only with ALF-world. This is a more challenging environment where instead of acting purely based on text, we have a visual environment. So they converted a text environment into a visual environment, making it more difficult to operate. This environment had very low accuracy for GPT, 4B, a visual language model, and instruct blip, and fine-tune visual model. For those that may not be familiar with ALF-world, it is an environment where the agent needs to accomplish a goal based on a series of sequences. The goals are daily tasks, like in a home environment, like picking something from the kitchen or finding a particular object in a room. The challenging part is that the location of the objects may not be known. So what they did was they followed a different approach. Instead of operating using exclusively a visual language model, they operated with a brain by a large language model trained on reflections synthetic data. Reflections is a learning algorithm, a prompt engineering technique that learns from their mistakes. It's verbal reinforcement learning. Let's see in detail how this learning process works. This is what they call cross-modality imitation learning. In the image, you can see that it splits in half, the training part and the inference. At the right, you see the reflection process. There's an LLM actor and an LLM critic, and two types of memory, the short-term memory included in the prompt and the long-term memory stored in a database, an embedding database. Through this cycle, by engaging and interacting with the environment, the actor gets increasingly better at resolving the tasks, and the prompts get updated accordingly. Now, this model is let's call it the alpha model, is the one that we will use imitation learning to learn from. So now it goes to the second part of the model where we do the inference. In here, we have a visual model that attempts to learn from the expert model. Here, the process that we follow is that we first convert the visual embeddings into textual embeddings. And these textual embeddings are decoded into goals that are able to be read by the expert model. And what we are trying to do is that the original visual embeddings, that the tasks performed on the visual embeddings are the same that the ones originally followed by the expert model. We will see it in more detail. So this is the step-by-step process for training EMA. It follows 4 steps. At the left, you see the pseudocode for the training algorithm, and at the bottom, you see the formula for the imitation learning. The first step, as I said, was to encode visual embeddings. So in the lines 5 and 6, you can see how both text embeddings and visual embeddings are generated. Second, we use a querying transformer to extract the most relevant visual features from the visual embeddings. What we want to do is to make as similar as possible the visual from the text embeddings. Once this training is completed, we draw a linear projection layer to align the visual features to the text embeddings. In this training methodology, this consists of learnable weights. So there's a process where the weights are updated. And finally, as we saw, the LLM decoder generates the action XA. This action XA, as you can see in the bottom, has a conditional dependence on the visual embeddings, SV, and what we are attempting to do is minimizing the loss from the imitation action to the expert action. And that is the actual problem that we are optimizing. And as we are optimizing this problem, the linear projection layer weights are being updated. And these are the results. This is why this paper is so impressive. In the left, we see the comparison between the visual and the text environments. We see the visual models, the language models, and the visual to language models. And we can see that for the text models, the top score is 91% by reflection, the training that we use to train our expert. But on the visual language models, we see that the top score, other than Emma, is 22% in struct blip. Other scores are 16%, 13%. For GPT achieves a 16%. And for visual models, the result is even worse, 6 or 5%. But Emma achieves a surprising 82%, very close to the large language model operating on the text world, where it achieves a 91% of efficiency. And on the left, on the chart of the top left, of the top right, we can see how the score approaches gradually from Emma because it's able to use the reflection verbal reinforcement learning to learn from the task as it attempts it again. So the big difference between Instruct Blip or other visual learning models is that by using the large language model, it can get the reasoning capabilities and attempt the task many times without updating the models. And this allows that increasingly through time, the accuracy gets better until we get to the 10th attempt, where we get a very respectable 82%. And in the top and in the bottom right, you will see the task decomposed by type of task. In particular, in this world, we have around 7 different tasks that can be executed, for which we have different scores. Awesome. That's how the training process works. Now let's explore some big ideas around this concept. And the first one that I want to talk with you is about imitation learning. How can we use this idea of imitation learning to create powerful applications that bring value to society? Well, a very financial one, but very simple, but very important, using less expensive versions of large language models. So this process of using imitation learning can be very relatively easy to implement for finding prompts that perform just as good as prompts in expert models. So we can get the prompt and the output on the very expensive large language model, and we can iterate until we find a similar prompt that may be slightly longer, but runs on a much more inexpensive large language model. And the savings we can get from this operating at scale become significant. Let's explore a second big idea around imitation learning, which is the automation of human tasks. Very obvious. By using imitation learning, comparing how a person does a task, the large language model can start to create this learning from it. One very simple example of this could be sales. So if we see that a particular human responds to a particular email in a particular format, then we can start imitating that process. Similarly for customer service, for recruiting, for marketing, for even product development. There are a bunch of different that we can gradually train agents to imitate humans. And of course, freeing us from the mundane tasks. Now, this one is very interesting, synthetic data generation. What it is about is that today, large language models are generalists. They operate on a wide variety of data. However, there are particular domains, in particular numerical data, where they do not achieve the same result that supervised models. So what we could do is to generate data, generate predictions using specialized supervised models, and through imitation, first create the synthetic data, just as in the case to React, and through this process, start training the large language model. And in this sense, the large language model becomes even more general. In the domains that today does not perform, does not excel, gradually it could be achieving more expertise. And there's many more. These are three that some of them very general, some of them very particular, what I propose where imitation learning can be used. But I'm hoping that you can share those with me on the comments. Now, let's go for transfer. The idea of moving from gaining insight in a text domain to operate in a visual domain. Usually, transfer learning is about using a model for some subset of data to apply it on a similar set of data. But right now we are operating on multimodal data. We are navigating from a language environment to a visual environment. This is taking transfer learning to a different dimension. And I will explore three types of data where we can move from one type of data to another. And the first is time series. So today we are not able to perform with causality, to make predictions through time. And this idea is relatively similar to the generation, but it's applied to the time series. So in this case, we can start using this prediction on time series data. It may be we can use the learnings from the time series to embed the agent with this knowledge of supervised learning. So how could we operate on a time series data set with the brain of a supervised time series model using a large language model? It may be difficult to see at first sight, but there's a powerful idea underneath. Similarly, recommendation agents. Again, today we have our recommendation agents that operate on numerical data, but a big drawback of them is that they do not incorporate either recent information that's not fit on the model, or subtleties captured in language that are lost via encoding that do not have the reasoning capabilities of large language models. So the idea would be to enhance traditional recommendation agents by first imitating the actions of the recommendation agents, of the supervised recommendation learnings, and only later apply a transformation of large language model reasoning skills to make recommendations. A second very powerful idea that drives hyper-personalization. And the final one is data analysis. And this one is particularly powerful because the data analysis ultimately goes into making decisions. But there is a gap between how data analysis is done and how decisions are made. Data analysis uses structured data that is highly numerical and highly automatic, robotized. But this needs to be translated into verbal decisions that are communicated either in emails, presentation, graphs, etc. So the process of bridging this gap between structured data and decision-making could be made by a model that learns from the data analysis realm to get conclusions and translate those conclusions into insights that can be directly elevated into decisions. For the spectrum of decision-making that goes from automated, fully automated at the lowest, to fully human-driven at the highest, we can take a step further into the automation of decision-making by using large language models and transfer learning from supervised models. And the final and third big idea that I want to share with you is using LLMs as a CPU, as a central processing unit, or even as a chief executive officer. And what I mean by this is that the model is able to orchestrate different tools that could be symbolic programmatic tools like APIs, like web applications, to accomplish complex tasks. In here, we are seeing how the visual information is simplified into a language that the large language model can use. And we have a similar idea here. How can we create this dimensionality reduction or simplification to allow the large language model to use its reasoning skills to execute and make different decisions across a wide variety of tasks? So in here, we are moving these new computation capabilities as the central piece of very complex multi-domain systems. I hope you are enjoying these ideas. And there's a lot more to go from here, but I would like to finish with some closing thoughts. The first are very precise applications on where we can apply this multi-step process of imitation and transfer learning into very precise day-to-day applications. And this is probably the biggest idea of all, which is creating simulated environments of product and marketing domains. So the big idea here is that today, when we are designing a product, we launch an experiment with real users. And even if we launch it to a subset of users, still our ability to experiment is relatively low. We may not know, other than intuition, how our users could react. But what would happen if we create this simplified world of simulation where we train an agent to act on a product and evaluate the capabilities or the new features of the product? This accelerates the feedback loop by a significant margin. And if we can even automate product development, we are talking about factors of 10, 100, 1000% the same. And similarly for marketing. Today we have posts like in social media, copywriting ads, that it becomes very expensive to experiment. But what would happen if we can create a simulation environment where trained agents can provide this initial feedback before we release them? That could drive costs significantly lower and increase efficiently higher. Very similar, we can change and transform how writing and media generation works. And the idea is very similar, to create a simplified version where we test ideas before going through the full process of writing. So for example, if I have an idea about a movie or about a story, I can start testing the structure, the emotional journey of the idea or the movie before writing the entire script. And maybe this idea is about a civilization in the space. But before writing the full script of what happens with this civilization, I may modify the structure to adapt into an emotional journey that adequately fits the audience that I'm targeting. And the final application, and this full credit goes to ChatGPT, is in education. I could create these two environments where one is a fully expert environment and the first one is a simplified environment. And we can enable communication between these two environments to use adaptive learning and gradually increase efficiency to teach higher level concepts in a personalized way. And again, you can see how we start moving from one very complex domain to a simplified domain, and how the transfer learning between the two domains, and the imitation learning between these two domains benefits both in terms of cost and efficiency. A second concluding area of thoughts that I would like to share with you are some very interesting technical details of the paper that I didn't dive deeper, but it may be interesting to do so. First, visual language model. In particular, the BLIP instructor visual model has more than 2,000 citations in less than 1 year. The GPT version is also very interesting on how these visual language agents work. And as we move towards more multimodal agents, this is a big area of research. The second, again, we covered it before a lot, but there are a lot of subtleties in imitation learning and behavior cloning. In here, they use a particular technique, but that doesn't mean that it's the best technique for every problem. And maybe an interesting area of research. The technique that they particularly use is called Dagger and direct preference optimization, which is a very famous method, which might be interesting to go into the mathematical details of how these learnable weights are tuned. And the final dive deep idea, which is my favorite, is how this linear projection layer works for transfer learning. There are very interesting ideas from the creation of the embedding spaces to how we actually map one space to each other, to even the philosophical implications of how these two embedding spaces could have different modalities or different kinds of information, either to perform better by combining both of approaches or by seamlessly moving between two environments. There's a very rich topics in how to translate between two different embedding spaces. And what I would like to leave with you is with questions. Some questions that today I wonder after reading the paper, after sharing these ideas with you, that I would love to hear from you. Either if you are an expert or a business person interested in how these applications can transform our world, I want to hear your opinions. First, again, I said it, how is these similarities on different embedding spaces? I'm almost talking about a topological view. How we can interpret the shapes in the visual environment to the shapes on the textual environment, and how we can model and tune the geography, the topology of the environments to resemble each other or to highlight the difference. Super interesting topic. Second, extracting the most relevant visual features. This particular model depends on the 2D embedding spaces being relatively similar. And for this, we need to first identify, and second, extract, and third, shape the most relevant visual features. So that process of identification and shaping is extremely interesting and may vary based on the different types of problem. How to do that? It's an open question that I would like to hear from you. This one is great. Symbolic planning instead of reflection. So in the previous video, we covered how to integrate symbolic planners for this same textual half word environment. What would happen if instead of using the reflection generated synthetic data, we insert a symbolic planner that is much less expensive and much more efficient? Would it drastically improve the results? How would that architecture need to change to integrate it? Interesting question. Zero-shot learning. The most challenging part of training Emma was updating the weights between the learnable weights in the visual embedding to the text embedding. But would it be possible to, using a visual language model, caption the images and translate this into prompts that can be modified or updated to be used by the reflection expert agent? In that way, we are achieving zero agent from visual to language model. I hope you can see the idea, very powerful idea, and it would be interested if this can be actually performed. And the final one, you know me, I'm a fan of the human brain, of our cognitive system. So how does this actual multimodal cross-modality works in our brain? How do we actually translate our auditory information into semantic imagination. Can we learn some insights from the brain? Can we achieve efficiency through learning from the brain? I'm certainly sure we can, and it would be very interesting to know how to do so. Thank you. Again, I'm Santiago. I explore big ideas on AI, and my goal is to build a community. I imagine a place where all these big ideas, these philosophical questions, these powerful applications, we can get together, not only imagine them, but eventually create them. Get to know each other, share our interests, and maybe push the boundaries of knowledge further. Thank you for watching. Your likes, your comments, your subscriptions are extremely important, helps to keep the channel sustainable. And until next time, goodbye.